Uh, I guess we are live, guys. Can you just let me know that we are live or not? And if my voice is clear, also please mention. Thank you. So, in today's session, we are going to solve division 2 plus division 1. So, let's wait for one more minute and then we will start. How many problems did you solve during the one test? Problem. I'm currently a student. No problem. Just look up the editorial now. So let's start with the post contest discussion. And no problem. We are going to solve up to E. Okay. So in in today's problem, I'm going with division 2 first. So this was the first problem of division 2. It says that you are given an integer n. You need to construct a permutation p of length n satisfying the following condition. Okay. So pi minus pi plus 1 of modulus is divisible by I for every I 1 to n minus 1. Okay. It can be proven that such permutation always exists under a constraint of the problem. Okay. So let's start. Just a note. So just one second. Okay. So in the first problem, you are given with an permutation and you need to find a permutation. So it's P1, P2, P3 up to some Pn. You're given with n. Okay. And it says when you are making this permutation, the difference between the adjacent element, which was Pi minus Pi plus 1, must always be divisible by I. Okay. So if I look carefully in this array or in this permutation, I can deduce that for P1, let's take for some example, say n is equals to 6. Okay, so 1, 2, 3, 4, 5, and 6. Okay, I don't know which numbers to put here, but I know difference between these two numbers must be divisible by 1. Difference between these two numbers must be divisible by 2, then 3, then 4, then 5. Okay, so let's not fill from the start. Why? Because for one there may be multiple combinations like 1, 2, 2, 3, 3, 4, 4, 5, and 5, 6. So there are multiple combinations to put here. So let's start from the last because for 5 there is only one uh, combination that you can put, which is 1 and 6. Okay. So I'm putting 1 here and 6 over here. You can start with anyone. Okay. So now I need a difference of 4 for this 6. Correct. So for the difference of 4, either I can add 4 or either I can subtract 4. So 6 plus 4 gives me 10 and 10 minus 6 modulus. gives me 4. Okay, or I can do 6 minus 4, which is 2. So 2 minus 6 is also 4, which is divisible. So I cannot put 10 here because 10 is greater than n, so I can put 2 here. Now I need a difference of 3. You can go again same 5. Now I need a difference of 2, so I can put a 3 here. And I need a difference of 1, I can put a 4 here. Okay. So with this, you can just make your permutation. And if you look carefully, there's a pattern like 1, 2, 3, and then 4, 5, and 6. Let's check this pattern for one more n, and then we can just confirm it. So let's say n equals to 7. 2, 3, 4, 5, 6, 7. Now put again 1 here, 7 here. How? Where? In this case, pattern or something. C can be done without binary search. Yeah, C can be done without binary search. So, any doubt? Okay. So let's start filling for n equals to 7 on. So I will put 1 here, 7 here. Then I need a difference of 1, 2, 3, 4, 5, and 6. So I will put a 2 here. Then I can put, I need a difference of 4, I can put a 6 here. Then I need a difference of 3, put a 3 here. Difference of 2 is needed, put 5 here. Difference of 1 is needed, put 4 here. Okay. So again, as you can see, it is 1, 2, 3, 4, 5, 6, 7. All right. Yeah. So what you can do, you can start filling from here. 1, n minus 1, 2, n minus 2, 3, n minus 3, and like this. Okay. So sorry, 1 n, n minus 1, then n minus 2, then 4, and so on. You can just fill like this, and you can implement it. It's very easy. You can just make 2 pointers LNR and start filling LNR. Okay. So this was the problem here. It was quite intuitive and easy. So is there any doubt, or we can move towards problem B now? Hmm. I assume this is clear. So let's move toward B. Okay, wrong answer in B. Okay. So in this problem, Cordell manages a row of n seats at something. Okay, where students are strictly forbidden from sitting next to each other. Okay, you are given a binary string S, where Si represents the ith seat is occupied by a student, and Si equals to 0 indicates that it is free. It is guaranteed that no two adjacent seats are occupied currently. Cordell needs to add more student until it is impossible to seat anyone else in the room. Okay. However, she wants to achieve this state with few students as possible. Your task is to calculate the minimum total number of students seated when it is impossible to seat anyone in the room. Okay. So for this, there is 5. Okay. So for this problem, okay, what we are given it is a binary string consisting of zeros, ones. Okay. So a string like this is given to you. Now you are asked, in this string, the one represent the seat is occupied, and 0 represent seat is not occupied or free currently. Okay. Now we need to place some student on these zeros such that no any after placing all the student, no other student can sit in this row. Okay. Now there is one condition which we have to note is no two students can sit adjacent to each other. Okay. Okay. Correct. Now how to do this problem? What is possible? Not sure. Maybe 1000, 1100, 1200. Not sure. Okay. So let's take a basic idea. Okay. If I am making someone sit, so this is my student, say this is my student, and if I'm making him sit somewhere, so how many total number of seats it will cover? It can cover a seat here and it can cover a seat here, correct? So total number of seat that a single student will cover is 3. Okay. Now let's say uh, there is one student already seated here. Here are some zeros, and another student is sitting here. Let's take that example 5. This one, which is 4 zeros 1, 4 zeros 1, and 3 zeros. Okay. So it was 4 zeros 1, 4 zeros 1, and 3 zeros. Okay. So we need to find the total number of places we can make students sit. So I know that a single student will cover one seat in the left and one seat on the right. So for this particular student, this seat is covered and this seat is covered. Yes or no? For this particular student, this seat is covered and this seat is covered. So I need to cover these 3 seats. Okay, there are 3 seats. So, and I have just declared that a single student can cover a total number of 3 seats, one on left, one which is currently sitting on, and one on the right. Okay. Is this problem statement? It's B of div 2. Okay, so a single student can cover 3 seats, so I can say these 3 seats can be covered by a single student, and I will place it here. Then there are 2 seats available here, so I have to place one more student here. I can place one here, and here 2 seats are remaining, so I will place one more student here. So what is the total number of students which are placed in this total row? 1, 2, 3, 4, and 5. So answer is 5. Okay. So what's the idea that you get after seeing this? What we can do? What we can do one thing that we can store all the positions of one, then start from 0 to position 0, and then go for each position I and position I minus I plus 1, and check the total number of uh, seats here. Okay, so the total number of empty seats. Check if right and left position has a 1. Mm, I didn't understood, like check if right and left position have 1. If not, then put a 1 here. Oh, I guess you mean this. So if you are standing here, check if this is 1 or this is 1. If it is not 1, then you have to place 1 here. Yeah, it's the same thing now. For each, it's the same thing. Like for each one, I know that the left and right is clear for that particular seat. Yes. So left and right is clear for this particular seat. So every student will carry 3 seats with them. Okay. It's the same thing like it's carrying three seats, one left, right, and okay. So the logic. Okay, so I'm telling you the approach now. You have to store all the position of one. Then and for 0 to position 0, calculate the total number of zeros divided by 3. For position I to position I plus 1, calculate the total number of 0 divided by 3, and then position n to position last n, and then total number of 0 divided by 3. Okay. For 7, answer is 3. 5, 6, 7. So what you can do, you have to place it here. So you will place one here. Then this will be covered, and this will covered by following one which you will place here. Okay, so this will be covered, and then you will place one here. So answer is, just check the ranges. Each visiting is might fail it. The pretest too. I'm not sure that I have any HKs. There must be no HKs. Like you are just doing taking from 0 to position 0, which is the first position of one. Then check total number of zeros, and keep in mind, guys, you have to take the seal value here. Okay, or for all three, take the seal value. If you don't take the seal value, it might give a wrong answer. Okay. If position array would be empty here. No, yeah, position array is empty for here. So for that, you can just put a condition like if position array is empty, then you do 7 plus 3 minus 1 divided by 3, which comes out to be 3. Seal value. Why seal? Because if there are like 5 seats, okay, now one student can take up to 3 seats. So I place that student here. So if you do 5 by 3, it will give me 1. But this is wrong now, because one student cannot fill 5 seats. But two student can fill up to 5 seats if I place one here. So the two student can take up to 5 seats. So I have to take seal value here. Right? 3 minus 1. Seal value. It's the formula of seal value. A divided by B, C, A divided by B. Right? But for 101 taking. Look, for 101, how many are there? Here, there is no 0, 0. Here, the difference is 0 and 2. Index is 0 and 2. So 2 minus 0. Then you do 3 minus 1 divided by 2. So it will give you, wait, 2 plus 2 minus 2, 1, sorry, 2 plus 3, 5 minus 1, 4. Wait, we can't place here. No? Why we are doing this particular thing? Just have to see that now there is at least 3 seats available or not. How can just you check for these two positions if there are no 3 seats available? It's directly, if there are 2 seats available in between, or either one seat available in between, then why do we need to check for these two positions? In your position array, you are getting I and I plus 1. You can directly check na, the difference between I plus 1 and I. If it is greater than 3, then only you have to place the student greater than equals to 3. Else, why are you placing the student, or why are you checking the particular condition? It might be not. Exactly. So iterating over all position directly is not correct. We should only see the difference of position. Yeah, at least, yeah. You have to check at least, it's basic validity, right? If we are already satisfied, why we need to check or place the student at that particular point? Okay. So this was the complete logic of question number B, and it's quite easy. What you are doing, you are making a position array, store all the position of one. I can write the approach here. So make a position array, store all position of ones. Okay, indices. You can store indices here. Check validity first. Okay, then do this thing which I have asked you. From 0 to position 0, check how many zeros are there. There should be also at least three zeros. Okay, that seal value with 3. Same goes for I and I plus 1. They take seal value of 3. Then position n to position total n, which means the last index to the total length, and take the seal value with 3. Okay? You can mark the places, then cannot search for all the consecutive zeros to the division by 3. Might work, I don't know. Where and C on it check index. Okay, we are coming to C. You can mark the places that you cannot state and store all the consecutive and do division by 3. Why do you need to like complicate it like that when it's so easy? Like, if I can write a pseudocode for you, take the position array, you can store all the positions in this. Okay, take a pushback, push all the positions here, and then first check if position 0 minus 0 is greater than equals to 3, and take your answer as seal value of position 0 minus 0 divided by 3. Okay, then you iterate from I is equals to 0 to position dot size. Then do the same thing, check validity first. If position I plus 1 minus position I is greater than equals to 3, then update your answer with seal value of position I plus 1 minus position I divided by 3. Then for at the end, check again if n minus position I, position n to be last, let's say m is greater than equals to 3, then take answer plus equals to same thing seal. Okay, this graph thing, no? And 4 empty spots. I need to set someone like this. Check it. Hey, look, if you have 4 empty positions, you just need to know that here someone is placed or not. Correct? If you are placing someone here and there is a say the string is completely this, okay, 0 0 0 0. So if you are placing one here, then this seat will be empty. Correct? Then put someone like this. Oh yeah, you can put someone like this or start by putting in this manner. Na? There are 3 zeros, so put 1 here. Okay, so for this 0, you need to check the validity, that is there any 1 coming up with respect to this 0. If it not, then put a 1 here, so it covers this string also. Okay. Okay. So if it is clear, we can move towards the problem number C. Good. So this is the C problem in which you are given with an array A of length n, For an integer k, we called it piggy if and only if it is possible to sort a in the non-descending order by performing some of the following operation any number of times, possibly zero. First, select two indices I and j such that the absolute difference between ai and aj must be greater than equals to k. Then you can have to swap ai and aj. Okay? You have to determine the largest piggy integer k. If such integer doesn't exist, output minus 1. Okay. So in this particular problem, you are given with a1, a2, a3 up to an, and you need to sort this particular array. Okay. And the sorting condition is you can sort you can swap two indices if ai minus aj is greater than equals to k. Okay. The audio sound like is this clear? Audio. Am I audible or is the voice fumbling or something like that? No. Okay. So we need to sort this particular array, and the sorting condition is you can swap two uh, elements only when the difference between both of them is greater than equals to k. Okay, great. So let me know one thing. What is the only condition when minus 1 will occur? Because I can take k as 0 also, and as you can see we can take integer k as and if we take k is equals to 0, then for all element 1 to 10 raised to power 9, the difference between arbitrary element cannot be less than 0. Okay, because it's taking the absolute difference. So I can sort at all times, like I can sort all the times. If an array is not sorted, I can sort it all the times by taking k is equals to 0. It's the minimum most k that I can take. Now, what is the only condition that minus 1 will occur? It will only occur when we can't choose k. And what is the condition when we can't choose k is array is already sorted. So I am writing here if already sorted, just output minus 1. Correct? Now, if this is correct, I can now work for the maximum k that is possible. Look, I need to make the array sorted. So say a1, a2, a3 up to an. So I need to make this sorted, and the operation is ai minus aj greater than equals to k. Let's open this inequality modulus. So it will say either ai minus aj greater than equals to k, and the second part aj minus ai is greater than equals to k. Okay. So I can write it like this. Now, we can not iterate for all I and j. It will give us TL. So what I can do, I can iterate over one thing, that is AI. Okay, I am iterating over AI. So this particular thing is currently something which is not known to me. Look, I need any value which is greater than equals to k, correct? So for what value I should choose for AJ, listen to my problem. What value I should choose for AJ such that when it's subtracted it from AI, the answer is always greater or answer is always larger. I have to take this value as minimum as possible, because when I'm subtracting, the second part is as minimum as possible, the answer will be as large as possible. Correct? I can't see chats, but you are not writing it. Right? For I have when I'm choosing AJ, then I need to choose ages as minimum as possible for this particular condition, so that AI minus that minimum value must be greater than equals to k, and it will be the best possible choice for me for any age AI. Okay, let's come here. So for AJ minus AI, now here the A minus B is happening. Okay, so A minus B. Earlier we were checking for B, now we are checking for A. Now from which value I should subtract AI such that the uh, remaining part must be greater than as greater as possible, so that it cross the line of K. So it's always be the maximum value as maximum as possible. So I can take a very large value, then subtract that particular AI from that, because AI is fixed for me. Then the answer is always as large as possible, and it cannot exceed more than that. Okay. So I know now for these conditions what I have to do. I will do AI minus the minimum element. Just remove this. So I will do AI minus minimum element, and for this I will do maximum element minus A. Right. Now I am please keep your concentration here. Now I need the maximum K. Okay. So the maximum K is what? The maximum value of both these AI minus minimum, comma the maximum value minus AI. Okay. Now you can just iterate over all the possible values from 0 to n and take this K as maximum of these this term. Okay. I'm not writing here. So the maximum of this term. But now you have to update your answer. Let's uh, take an scenario where you have A1, A2, A3, okay, and so on. I'm currently taking A1, A2, and A3. Let's say the max, just think logically, some AI minus minimum, okay, comes out to be X. Will this X sustained for this A2 also? Or will it change? Will it grow or will it become less? Tell me. If I increase my A2, oh, if A2, if A1 is less than A2, so this is the case. If A1 is less than A2, so I'm changing A1 to A2, then will it increase or decrease? X will increase because I'm subtracting the minimum possible value. And if I increase this, X will increase. Same thing here now. The max minus A2, okay. Now max minus A. Let's say it comes out to be Y. Now same thing. If AI increases, the Y value will decrease. Yes. So for these particular thing, one increases and one decreases. So what is the optimal way to choose if I want to update my answer with the certificate? If I need to update my answer, what I have to do? Do I have to do a minimum or do I have to do the maximum? I have to do a minimum. So minimum of answer comma. So that's it. the whole problem. So this is the code. This 4-line code is your problem number C. So you always take minimum because it keep on decreasing, and your k depends on this term also. Okay, I will message Shyam. Is this clear? Problem C. We can just okay. Is this clear? So if it is, we can move towards the problem number D. Or any doubt in this? Any doubt, or we can just move to D? Clear. Okay. So let's move towards the problem number D. Yes. Yes, C was too easy for because C was division 1A, so that's why this time it was easy. So if it was normal F2, it might be a little hard, little more hard. Okay, so now in this problem, you are given two negative integers x and y. Find two non-negative integers p and q such that p and q is 0 and absolute difference of x minus p plus absolute difference of y minus q is minimized. Here and denotes the bitwise AND operator. Okay. So very small statement. So in this problem number D, you are given with two values x and y. Okay, I'm not writing here x and y. Okay. You need to find two values p and q such that p and q is 0. Also, the absolute difference of x minus p plus absolute difference of y minus q is as minimum as possible. Yeah, D was constructive. So look, let's first organize for the first case. Like, what if x and y is 0? If x and y is 0, then I can put p as x and q as y. Then p and q will always satisfy the condition of 0, and x minus x and y minus y is the minimum most possible, okay, which is 0. Okay. Okay. So for the first case, I can say my answer, the best answer can be x and y. Okay, so my best answer is x and y, and my current p is x and q is also y. You can just make it y, and y is all with x and y, so it will give you the y. Okay, so this is my case one. Now let's run for some more cases. Wow. Now if p and q need to be 0, it means there must be no position I where the bit is set for p and bit is set for q2. So this position must not happen. So if in X there is some bit where let's say this is X and say this is Y. So as you can say, at this particular position, these bits are set. So what I have to do? It's easy. Either set this bit in P and unset in Q, or vice versa. Okay, correct. Either you can set this bit in P or you can set this bit in Q. So I can write my P as 10 110 011, and I am setting in this bit in Q. So 001 0. So this end will be give me 0, and the answer is minimum for some test cases. For some test cases. Okay. So this is my second case which I can think for this problem. Okay. Now coming to the case number 3. Now for this case I take a very good example for you, which is x is equals to 7 and y is equals to 7. All the bits are set. Now if I take the scenario which I have taken for case 1, which means if I set 1 here and these two 0, or 0 here and these two 1, the output for the equation output, which was x minus p and y minus q, it will comes out to be 7 minus 4 for this, and this comes out to be 7 minus 3. So this is 3, this is 4. So the summation is 7. Okay. So is this the minimum summation that can be possible? No. You can go a much lesser summation by taking p is equals to 8 and q is equals to 7. So this will give you 7 minus 8, which is 1, and 7 minus 7, which is 0. So answer is, your answer comes out to 1. Correct. You can you can do a much better thing also here by taking 111 and 000, and this will give you an answer of 7 again for the case 1, which I we talked about. Okay, but now to do this, what we can do? I am taking p as 8, which means 1000, and q was 7, so 111. And vice versa is also possible, so you need to take care of that. Okay. So I know that one term will be q is equals to y or x is equals to p. So one term will be same, and for the second term which I will take, if I am taking q as y, which is same, then the second term will be I will check from the MSB, which is the first 0 I encounter. Okay, the first 0 I encounter, set that 0 and change remaining part to 0. Okay, so what I am doing, if this is 1 and a 0 comes here and there is something. Okay, so what I am doing, I am putting 1 here and unset the whole part. Okay, so this is I am doing for either for p or either for q. You have to check for both and take the minimum answer that comes out. So this was case 3. This case stucks on one test case which I got while submitting it. Case number 4, which is what if the number is 2 raised to power something, or take 4 and 4. This was the test case that it failed. So if x is 4, it's 100, y is 100. Okay. So now let's try all the above cases which we have done. So if I try case number 2, set in 1, so p will be 100, q will be 000. So it is 4 minus 4 and it is 4 minus 0. The sum comes out to be 4. It's not been. Try the second case, take one value ahead. So this is first case 2 and this is the case 3. I'm taking one value ahead, so 1000. Then q will be 0100. For this, it is 8 minus 4 and this is 4 minus 4. Still consist 4. Now, in this case, what we are going to do? We are putting p as same value. For this particular case, where the power is 2. Okay. And then we are putting q as unset this and set both of them. Now, it is 4 minus 4 and this one is 4 minus 3. Now the summation is 1. Okay. You have to do a reciprocal thing for this also. Okay. Take reciprocal of this. Reciprocal and say, swap the numbers vice versa. So you have to take q 100 then p as 011 and check for this also. Because it might be possible that this will give you a better answer. So here we discussed 4 cases and you have to take care of vice versa of each of them. First one is quite easy. You have to, if x and y is uh, x and y, which means bitwise and is 0, then you can just directly take p is equals to x and q is equals to y, which will give you the minimum sum possible, which is x minus x and y minus y, which is 0. Case number 1 will be, you can set one bit in some p and unset that in q, or vice versa, set in q and unset in p. Okay. Case number 3 was, if there are all the bits set, you have to set with where case 2 fails, you have to set one one on the most significant 0 and then unset all the bits ahead of that, and for the second one take the same value as y or x. Okay. Then case number 4 was when both case 3 and case 2 fails, then you have to do the bit which is set in some x, take that particular bit and set it, and remaining will be unset. And for all the zeros which were inside x which were unset, you have to place one in there. Okay. So it will make y and x p and q as minimum as possible to get your answer. So check for all 4 conditions, then your code will run easily. So this was the approach for D. Any doubt in this? Any doubt or any query, any doubt in this problem or anything which is not clear? I can explain it. Not mention when we can move towards the problem number. Repeat the normal case different numbers. Case number 3 or 2. I'm going to restart from case number 1. Okay. 50 different numbers about. Look, if x and y is 0, then you can just directly put p's as x and q as y. If it is not 0, okay. So in this case, like if x and y is not 0, so this is my case 2. There is only one bit which will be give you a conflict. Okay, there will be only one type of setting which give you conflict. It's the same bit which is set in both of them. Okay, so a single bit which is set in both of them which will give you conflict. Else, if it is 10 or 01 or 00, these three will give you and as 0. So we don't need to touch up both of them. Okay, thrice of them. Okay, so we need to work on only this kind of bits. Okay, as you can see in this particular scenario, this particular 1 1 gives conflict, and when we will do AND, it will become a headache for us. So how can we remove this one? We have one approach that put 1 here and put 0 here, or put 0 here or put 1 here. And why are we are not putting 0 zeros? Because if we put 0, the value of the number will decrease, correct? Both of the value will decrease, and we have to pay some cost for that, which means uh, I can write it here. I'm writing with green. So when you do x minus p and y minus q, if you decrease any of these two values, you have to give the particular cost of this particular I. Because if you are putting 0 on both of these, uh, 0 on both of these value, it will definitely give you end as 0, but it will take some cost. The cost will be 2 raised to power I. So this equation sum will increase by 2 raised to power I. That's why we are not putting 0 0 in any of them. Okay, so here, so I can put either 1 0 or 0 1, correct? So if I'm putting 1 in this and 0 in this, I have to check for the equation. Look, I can write it. So for the case 2, it might be possible like for x is 1 0 1 0 1 0 and y is 0 0 1 0 1 0. Okay, so this is our x and y. So you can make p by this is not a conflict, so take it. This is not a conflict, take it. This is a conflict. You have a choice to take it or not take it. I'm taking it. Okay, in the p. This is not a conflict. This is a conflict. Take it, and this is not a conflict. So now q. Q will be if I'm there is not conflict, no conflict. There was a conflict and I have taken in p, so I'm not going to take in q. So q will be like this. Now check for this condition. Okay, so this will be your answer dash. Okay, now you have to check if this answer dash is minimum or not. Now swap them. Now this time for p you are unsetting the same bit. Okay, so this was not okay. So for this no conflict was there, so take this. No conflict, take this. There is a conflict. In the previous scenario I have taken that bit, now I am not taking it, so no conflict here. Conflict here, I am not taking it, and no conflict. Okay, now here your q will be no conflict, no conflict, conflict, no conflict, conflict, and 0. Okay, so this is your next take. This is p1 q1 p2 q2. Now check again, check for this particular equation. this will be your answer dash dash. Okay, so now check this answer dash dash, which is minimum. Okay, update it. So this was your case 2. Okay, this case will fail on some certain conditions, and you need to know that particular certain condition. Okay, so that was intuitive. That was an intuition. Okay, this is intuition. Now I need to check that where this case fails. Okay, this case fails when you have all one set. Okay, all these one set. Now you don't have any value. So if you are doing like this, take this and don't take this, take this, don't take this, take this. Okay, so if it is x, it is y. I am just taking it random, taking and noting. So if I am taking in p, I will not take in q. If I'm not taking in p, I will take, notate, take and notate. Okay, so this will be your p and q. But does this give you a better answer? I guess this is 31, 16, 1, 2, 8, 16. So this is 31. So it is 31 minus, what is this value? 16 plus 4 plus 5, 5, 16 plus 5, 21. This is 31 minus 21. And this is 31 minus 8 plus 2, which is 10. Okay, 10. So this will give you 21, which is 31. So this is not optimal, right? What is optimal? That if I take P as 32 and Q as 31. So in this scenario, 31 minus 32 plus 31 minus 31 will give me 1 plus 0, and it is 1. This is optimal. Okay, so my case, my intuition failed in this particular case. This intuition failed in this case. Okay, so for this, I need to make, sorry, for this case, I need to make this particular P. And to make this particular P, what I am doing, I am marking the first 0 coming from MSB, because there will be multiple zeros here. So the first 0 that I encounter, I will mark that as 1 in X, and the rest will be converted to 0. Okay, so this will give me the number which is just larger than X. Okay, so it will be X plus 1. Okay, and Y will be same, which means Q will be same as Y. So either you are doing this make X to X plus 1, which means P is equal to X plus 1 and Q as Y, or make your Q as Y plus 1 and X as P as X. Okay, so check for both of them with the same equation which we had, X minus P plus Y minus Q. This will give you answer triple dash and answer 4 time dash. This will give triple dash, this will give 4 time dash. Check which is minimum with the same answer. Okay, keep taking minimum of them. Okay, so this was my satisfying case for which fails for the case which fails for case 2, satisfied for case 3. Okay, now is there any number which makes this case 3 fail? There is one, which was 4 4. X is equals to 4, y equals to 4. So I can write x as 0 1 0 0, y as 1 0 0. Now if you try both of the cases, case 2, by taking 1, so p will be 1 here, q will be 0 0 0. So your answer was not can we discuss the wait, we'll discuss it. So for this, your answer will not be the minimum, it will be 4 minus 4 and 4 minus 0, which comes out to be 4. And if you take case 3 approach, in which you make your p as 8 and q as same 4, then here also it is 8 minus 4 and 4 minus 4, still 4. So for this particular case, you have to make some intuition that what will be the minimum answer for 4 and 4. It will be, if I take P as 4 and Q as 3. So how can you make this? You can make this by taking the MSB bit as 1, and the places where a 1 is there, sorry, the places where 1 is there, put 1 in P, and where there are 0 in P, put 1 in Q. Okay, so this will be made. Okay, yeah, these are only 4 cases. uh, when I solved this problem, I made this intuition and case 3, and I have submitted that, and it will get wrong answer on test 1. Then I got to know that for 4 4 the answer is wrong, and I am getting this particular answer which was 4. So I need to minimize it. So how can I minimize it? Then I thought that if it is 4 4, now the only condition that's why it's failing is 2 raised to power k. So I can put 1 in P and rest 0 zeros as 1 in Q. Okay, so that's why I can just able to submit it. Okay, so this was the whole approach for D. Is this clear? Was the difficulty in this? What if one set is 1? Yeah, you need to look at all the 4 cases. And implementation was quite long and a little bit complex, not very, but a little bit complex. If you missed a single step, it will throw a lot of errors. But it's not possible if you are not, if in P you are setting 1 bit and at the same place you are setting 1 bit in Q, then P and Q will not be 0. Okay, so it might be there something like there 1 bit is set in P and unset in Q, or set in uh, Q unset in P, or both of them are 0. But we don't take both of them as 0 because it increases our answer by 2 raised to power I if ith bit is conflicting. Okay, is this clear? And see, like there are no two. Why did you evaluate this, especially when it's x or y is 0, x and y 0. If x and y is 0, then I can directly take p as x and q as y. Where in what case x and y was 0? Here x and y is not 0. Here x and y was not 0. Here when I take in 1 1 1. In this case, x and y is not 0. If x and y is 0, there is no conflict. Can you dry run on this? I can dry run on this, but it will take a lot of time. Can you take a smaller number or 3 to 1 if there is a lot of bits? Provide bits for 1 to 3 also. Again, 1 to I will write to be. It will be, I can write it 4 plus 32. This is 96. 96 again add 16. 96 is 2. You can add 8, 1 to 0. Then you can add 2 and 1. Okay. 1, 1, take this. This is 123, I guess. Yes, 3 to 1. 2, 5, 6. And I want to get now. 4 will give me 3. And take now. Okay. This is 1, 2, 3 and 2 to 1, right? Yes, I'm not wrong. Okay, so there are only two conflicting bits. One is at, say, this is position 0, 1, 2, 3, 4, 5, and 6. One is at sixth position, one is at zeroth position. Okay, so first of all, x and y is not equal to 0. Okay, so we will try from our case 1. So what is our case 1? It says take ps 0, 0, take this conflicting bit in p. So which are not conflicting, take all of them, and then take this bit in p also. Then for q, the conflicting bit will be 0. Okay? So this is 1, this is 0, 0, 0, 0, 0. Okay. So this is 1p and 1q. Same, do a vice versa thing for this, which is don't take in p this time. 1, 1, 0, 0. Q will be 1, 3, 4, 5, and okay. So this is for your case 1. Check answer from this. Okay. You can take a screenshot for this bit set. I'm not calculating what is the number. Okay. So you can just take x minus p plus y minus q for both of them. For both of them. So now take for case number 2, in which I will take p as set this particular bit. Okay. So it will be 0, 1. How many zeros? How many? 1, 7. Okay. 1, 2, 5, 7. So this was the number. Yeah? So this will become 128 and q will be your 321 only. Okay. So this is your p and q for case 2. And do a reciprocal thing for this also. This will be your same number. 0 0 1 0 double 1. 4 times 1 and 0 times 1 0 double 1, and q will be your 1 here, and double 0 all 0 second. Okay, so I guess 8 zeros are there. 4 5 whatever it is. Okay, so take the same equation, x minus p plus y minus, and what you are saying, right? 128 and 321, right? So this is 128 and this is 321. So for case 2 you can get the minimum answer. Then try for case 3. You will get a you have to try for all these cases which I have talked about, right? So this was case 4, this was case 3, case this was case 2, and case 1 was false, so we are not taking it. So try for case 4, in which we are setting one bit in p and one bit in q. So these are non-conflicting bit. Mark them as 1. Oh, sorry. Mark this is 0. This is 1. Then it was 1 here. Then all these 1 will come. All these 1 will come. Yeah. Set this bit as 1 and it will become 0. And for q, uh, unset this bit, and all the bit will be set in 1 here. Okay. Set these bits, and do a reciprocal thing for p and q also. Okay. Actually, so you can just solve this for second test case also. So, so this will give you the minimum answer. Here I got the minimum answer which you are talking about 128, and this was 3 to 1 0. Okay. So you need to consider these three cases. This is clear. Now we can move towards the problem number E. Digit TP. Digit TP is for counting. I don't think like digit. Uh, you're like no, digit TP is for counting, right? You just count the numbers. Here I'm forming a number. Maybe you do some kind of changes in that network. I'm not sure. As for me, I might not do a digit TP. Now let's move towards the last problem which we are going to discuss. And it's a quite hard problem, like literally hard problem. So Jerry and Tom. In this problem, you are given with Jerry and Tom are playing a game on a directed graph G with n vertices, numbered from 1 to n. For every vertex 1 from u to n, there is a directed edge between u and ui, v plus 1, which means there is an edge between 1 to 2, 2 to 3, 3 to 4, and so on. In addition, there are m extra edges. The ith extra edge goes from ui to vi, where 1 to ui is less than vi is less than equals to n. The graph G has the following special property. There do not exist two directed edges, ui to vi and uj to vj, such that ui is less than uj and vi is less than vi is less than vj. Okay, so if this condition is true, these two edges cannot be there. T might be 17, 18. or 19, maybe 19. At the beginning of the game, Jerry and Tom stands on the vertex x and y respectively, where x is not equal to y. The game proceeds in turns. In each turn, player must behave according to the rules, and Jerry going first, followed by Tom. Jerry must choose one outgoing edge from the current vertex and move along to its end. Okay, so it is must, which means if Jerry has a edge which is going outwards, so it have to move in that edge. It don't have a choice to stay. But if there is no edge, then he can stay where he is. Okay, but Tom may have a choice. Tom can stand on the particular uh, in vertex and wait, or he can move uh, to the outgoing edge, move to the outgoing, or choose not to move and stay where he is. If at the end, at any turn, Jerry and Tom are in the same vertex, including the vertex N, the games end immediately and Tom wins. Otherwise, if Jerry is initially as vertex N or reaches vertex N by at the end of any turn, Jerry wins. Okay, so Jerry will reach N, so Jerry wins. Note that if after a turn both Jerry and Tom are vertex N, then Tom wins. Okay, so at any point of time, if both of them are at the same vertex, the Tom will win. Doesn't matter the vertex number. Throughout the entire game, both players know each other's location. It can be proven that the game will end in a finite number of turns. For a pair of integers, one is less than equals to x is less than y, y is less than n, x is not equals to y. Define fxy as follows. Jerry and Tom will play a game where Jerry start at vertex x, Tom start as vertex y. Tom wants to win, so but he also wants to minimize the number of times he moves. Okay, that is the number of turns in which he changed vertex. Staying still doesn't count as a move. Assuming both player play optimal, let fxy is equals to 0. If Tom cannot win, okay. If Tom cannot win, the fxy is 0. Otherwise, let fxy be the minimum number of moves Tom takes in order to force a win. If Tom wins under optimal play, Jerry will still try to maximize the number of moves Tom has to make. Okay, so both of them are playing optimally. Jerry wants to maximize the number of moves. Tom wants to minimize the number of moves. And note that if Tom cannot win, then we have to add a 0 in our answer. So we have to compute all the possible pairs. So take the sum of all the possible pairs from each of the vertex on the tree. Okay. So this is the question. It was a quite large question. Okay. So let's start with imagining that we are given with the nodes. Okay. So the nodes are given, and if Tom wants to catch Jerry, there is only one possible thing that will happen. First, we have to know that the uh, structure that will form after we connect all these edges. So if we try to connect all the edges, let's take some example. I can take an example from here. 8 is less than 8, 3, and 4, 5, 8, and 2, 4. So example is 8, 1, 8, and 4, 3, I guess. 2, 4. So first connect these edges. So take, there is a certain edge from 1 to 4, then edges from 5 to 8, and then is okay. Now there are also edges from 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, and 7 to 8. But we have to take care of that condition if we are joining u1 to v1 and u2 to v2. This condition must not be there, like 1 is less than u2, less than. 1 is less than v2. Okay, so let's join this vertex 1 2. Can I join this vertex 1 to 2? No, because there exists a vertex which is larger, so the 4 exist here, correct? And we check for all these uh, vertices. I have made the tree already in my notebook, so I can just try. Yeah. So the tree will look like the node is 8 and its children. So it was like this 5, 7, and so this will look the structure will look like this. And when you look carefully, each of the this graphs, each graph will look like a tree, okay, which will be always be rooted at n. This will always be rooted at n. So you can just say if Tom is at any value x and Jerry is at any value y, they will move upward to the root. Okay, so this is the main observation that you can see, right? So your graph is a tree. Now, your graph is a tree. What is the condition when Tom will win? If it is a tree and we are moving upward, Tom can only win at one certain condition, which is if Tom, these are the depth levels. Okay, so the depth of Tom, so the depth of Tom must be less than is equals to depth of Z. This is the only condition where Tom will win. Yes or no? Because if Jerry is above Tom, which means if Tom is here, Jerry is here, and Jerry is moving first, Jerry will go at the 5, then Tom will move to 4, Jerry will go to 8, and Jerry will win, and Tom cannot. So if Jerry is either one step above Tom, then uh, Jerry will win. Okay, is this clear? Right. So the winning logic is this, that depth of Tom must be less than equals to depth of Jerry. Right. Now we have to minimize the number of moves. Okay, first we have to minimize the number of moves. Okay, so we are choosing some conditions. Okay. In while we have to minimize the number of moves, so take care of this thing that Tom must be above Jerry, and if so, if x y when your Tom is below Jerry is will be 0, and for rest of the x and y we have to calculate the cost. Okay, so we'll calculate the path cost that will travel by Tom. Look, say for example Tom is on node u, and node has a sub this one has a subtree, so there is a subtree and it is a at level x. Okay, and Jerry is not in this particular subtree. This condition is satisfied, but Jerry is not at this subtree. That might be at some particular subtree which was uncle's or grand uncle, okay, or great grand uncle, whatever. So Jerry is at some vertex B, which is at depth y, and x is less than equals to y. So at which position Tom can catch Jerry? At which position Tom can catch Jerry? It's the LCA of both the nodes or not. If it is the LCA of both the nodes, the point where both of them connects, I can say the total cost that Tom will traverse will be my depth of Tom minus the depth of LCA. Correct. This is the total cost Tom will move. Great Danish by. Okay. So Tom have to move these many number of steps for E. Oh, sorry, for a particular U and B. Correct. Yes or no? I'm not a graph and not a tree. Did we do something? Look, it was written as a graph. It was written as a graph, but when you draw the edges, it will look like a tree. It will always look like a tree. Correct? So now one thing comes that we cannot compute this particular thing for each node. Correct? Instead, we can do one thing for each particular node. I can check how many winning edges are there for each particular U. How many winning games are there, which means the total sum of games which are below the subtree, and it will be stored into U. Okay, so this will give you a time complexity of n square. So you can reduce it by using a DSU and Fenwick tree. Take it. You can store all the possible values where the games end using this at particular node at each particular node. Okay. Correct. So you can just update your answer with this particular cost at that particular point at every node you. Okay. Now there's one more thing. What if Cherry is at a subtree? There is a at the subtree of U. Tom is standing at U and Jerry is at the subtree of U. Then what will Jerry do and what will Tom? In this particular case, Jerry will move and Tom don't have to move. So we will subtract. the count of games where Jerry was inside the subtree. Because if Tom is standing here and Jerry is something here, so Jerry has to move. No? Jerry has only one choice. Jerry has to move. Jerry will directly come to Tom and it will, you know, get caught. Right? So my final formula will look like answer is equals to your total cost where depth of Tom was less than equals to depth of Jerry minus the invalid games or where invalid games which we have talked about where Jerry was at the subtree of you. Okay? Jerry at subtree. So this will be my answer and I will update. I will take plus equals to correct. Now I can try run on one example. I will not completely try run because there are multiple edges and it will take a lot of time. For this particular example, 8, 5, 7, 6 edges. Right? 6, 6, 4. So x and y will change for all particular nodes. Like if x is here, y can be here, y here. Y is for Jerry. Okay? So x is for Tom and y is for Jerry. So y can be here all these particular nodes, or y can be here also. So there will be a lot of steps. Let's take for some steps and let's understand how the code is working. Now, say that my Tom is at x 7 and Jerry is at 6. Okay. So, how many, uh, rather than I can just say like this, let's take a complete example in which Tom is standing at 6. This is Tom. And check for how many particular Jerry's are there. Okay. So, how many Jerry's are there? So Jerry can be at this particular position, Jerry can be at this particular position, this particular position, this particular position. Okay. So why I'm taking only these positions because here only depth of Tom is less than equals to depth of Jerry. Okay. So only for this condition when Tom is at 6, there are 4 cherries that are possible, or Jerry can also be here, 5 cherries. So I can say the cherries can be at 1, 2, 3, 4, and 6. Correct. So how many total nodes are there? 5 nodes. Okay, so my answer will be increased by 5. Jerry can be at these 5 positions. Okay, so answer not answer, contribution means you have to multiply with the length also. Yeah. Now, how many Jerrys are inside the subtree of Tom? There is only one Jerry that is inside the subtree of Tom. But wait, if Tom and Jerry are both at the same position, will Tom catch Jerry? Yes, it will catch Jerry. So it will not be counted when x is equals to y. We will only count the terms where x is not equals to. So how many Jerry are at the subtree of Tom where x is not equals to y? There is 0. So for this particular the contribution is 5. Yes or no? Right. This live chat just turned off. So this was the problem. Okay. So you can take for one more example, like erase this. Sorry, not this part. Okay. So let's take my Tom is here. Then what are the all possible positions of Jerry? Is this, 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 and this. The total number of Jerry's are 1, 2, 3, 4, 5, 6, 7. So 7 Jerry's are there. Correct? But how many Jerry's are in the subtree of Tom? 5. There are 5 Jerry's in the subtree of Tom. So I will subtract it. So I will get a 2. Okay. So when Tom is at position 5, there are 2 Jerry's and there are 2 games conditions where I will win. Okay. And you can try run on all the possible cases. And when you take the sum of this, uh, take sum of all the cases, you will get a value 23 as your answer. So this was the problem. Now the implementation part is quite tricky, or it's very hard to implement because I was not able to submit this problem, but I was able to write the code at, like, before starting the stream, just before starting the stream, I finished the code. It was a BIT. I made a BIT, and I've used a DSE to store all these values where how many games are being played. Like for 5, how many wins are there? Because I cannot just iterate for all X and Y. Yeah. So we had two total nodes where depth is less than equals to tau minus 1 overall in this question. Depth is less than equals to tau minus 1. I don't understand. Like depth is no, not depth of tau minus 1. What you're doing is you have to first consider this is your winning condition. Like depth of Tom must be less than equals to depth of Jerry. Okay. Now you can calculate the total number of positions, like total number of positions where this depth is less than equals to like number of moves that we have to made directly, like the total number of Jerry's that you can also calculate in one go, or you can pre-calculate it. Also, you can pre-calculate the total number of moves that Tom will take. If it is not in the subtree, it is just depth of Tom minus LCA, depth of LCA. Correct. So this is the total number of moves Tom will make. You can also pre-compute it. Okay. Now, the thing that comes in the picture is if Jerry is in the subtree of Tom, then then your answer will be subtracted by some value. Because in this particular case we are just multiplying all the values, but we have to subtract these values because in this case Tom don't have to move. Tom can choose not to move, and this will make your answer correct. Okay, so this will be the optimal way, not the answer. This will be the optimal way. Don't make the Tom move. Let Tom be here. Okay, and Jerry will come from here, here, and here because Jerry has to move and Tom has choice not to move. Okay. So it will get caught at the second step automatically, and then the number of moves is 0. So you have to subtract that part. So that's it for this particular problem. If it is clear, we can just wrap up now. And what you are saying that if depth is less than equals to Tom minus 1, I assume you are thinking like, complexity you are referring to. Because you are doing two data structures and we store depth and LC. You can store depth and LC, but I have wrote this formula for this part. You need to know that how many invalid games are there, correct? So you need to store each of the invalid game and each of the sub index, and I will ask myself a query that, like, at which position to which position the I can win, something like that. And to store this particular thing, what you need to do is, when you are querying it, you store the count using the fan victory, and a DSU will be implemented. You can make a DSU, or without DSU it will also work, I guess. It will work without DSU too. Okay, so you store the values using a fan victory and then do this implementation. It is hard because it was like, for me it was hard. I had to do a lot of, at that time I was thinking a lot of things. That's why I guess it was, for me it was a little complex problem. Nothing else. So let's wrap up today's problem discussion. I hope you have enjoyed this discussion, and please support the channel by subscribing, and please, if you are able, take membership from the channel, and it will help the repo web grow, and also the special streams and special videos you will be able to access it. And thank you for joining. Have a nice day ahead.